right, welcome everybody. I'm very happy for you to be here today. So today we're going to talk of CNCs. Most of you might think, okay, CNC is just a botnet. No, it's actually an acronym for computer numerical control machines. Those ones are huge machineries that you can find everywhere in the industrial world. They are used to produce anything. So anything you can think about are basically produced nowadays either from CNC machines or from industrial robots. So those are the two macro categories of machineries that you find deployed everywhere. And they, as you can see, they are kind of complex. You know, these machines might cost even millions of dollars. So that makes them kind of interesting target to look at, especially for criminals. And given such importance, we decided, you know what, no one before us has ever looked into such devices. So let's jump into that, take a look and see how is the general security posture of those machines. So to give you a kind of introduction and to contextualize things, we are nowadays in so-called Industry 4.0, which is basically machines that are connected either to the internet or to devices that or servers that are used basically to manage such machines. And this is very much needed for controlling the production. So if you want to optimize the cost, you need to know what the machines are doing. So you are monitoring them, you are collecting telemetry data, and you can also directly influence the machine. So, for example, program a machine remotely. So those machines run with programs, and you can push the code on the machine and ask the machine to do anything specific that you want. And here in Europe, the European Commission is heavily pushing for Industry 4.0. So nowadays, if you buy a machine that is Industry 4.0 compliant, you have a discount normally from the reseller. And as a result of that, most of the vendors normally decide to go with an Industry 4.0 machine because on top of having features, it's also cheaper in terms of potential tax reduction. So when it comes to this ecosystem, it's kind of complex. So we can model the deployment of a CNC machine as a supply chain. So you are a vendor and you want to buy CNC machine. So where this machine come from? There are different steps. So there is normally a developer, a manufacturer who develop the so-called controller. So the guy on the left, the NC, stand for numerical control. So those one are vendors that develop the board, which is basically like the engine of a machine, and it's basically the core component of the machine. Normally what happens is that such vendor, they sell the controller to other vendors that then use to build the machine itself. So it's a bit like in the car industry. There are multiple players involved, and you can think that when you develop a car, you might buy the engine somewhere else. So here is exactly the same. What happen often, you have like one manufacturer of controller that sell his controller to 10, 100, even more vendors of CNC machines. So there are multiple vendors of CNC machine that use, for example, the same controller. So what happens when these machines get a reseller and get integrated into the shop floor? The integrator is basically the gentleman that take the machine, configure the machine, and install the machine. And then you have an end user that basically use the machine in production. So we decide to focus our research at the beginning of the supply chain for different reasons. First, as I said, there are not so many developers of controllers, because often we see machines that run with the same controller. So if we do a research there and we select a number of controllers, we'll most likely reach out a broader audience. Second, if there is a problem at the beginning of the supply chain, the problem normally gets propagated down. So for example, if there is a bug there in the code of the controller, then all the machines running with the same controller are affected by the same bug. Also, when it comes to technology, a decision made in the first step, for example, on which protocol to use, will impact everybody else. So if a controller manufacturer decides to use a certain protocol, then the machine developer need to use and comply with such protocol. So being at the beginning gives us the possibility basically to look into all the supply chain more easily. So what we did, we looked into 4 representative vendors of controllers. So we look into one controller from Europe. It's us. It's based in Germany and is one of the, Heidenheim is based in Germany, is one of the largest manufacturer of controller in Europe. Then we have 2 manufacturers from Japan, which are a market leader on the market. One is called Okuma, one is called Fanuc. Fanuc is also very prevalent in the world of industrial robots. And then we look into Haas. So Haas is the same vendor, but also it's also owned like the Formula One. So if you are passionate into car racing, you might know Haas for being like a team into the Formula One auto, sorry. And so interesting things for each of this. We look into both simulators that are basically the controller in the software version of the controller and machines itself. So another interesting aspect is, for example, Haas, which is the first one. As you can see there, Haas produce both machines and controller. So for example, as you can see there are different numbers. So we took a look at the Haas 100, and the machine. While other vendor, for example, Heidenheim, only produce controllers. So we look at the Heidenheim controller, but then we look at to a Hartford machine. So that's a typical situation in which the controller manufacturer is different than the machine manufacturer. So to give you an idea of how this machine looks like, you have a machine on the right side of the screen and you have a controller on the left side of the screen. So the controller can be fully virtual, for example, running in a virtual machine. For example, Heidenheim provide a virtual version of a simulator of a controller simulator, while Haas, you can see here, give you basically provide an hardware version of a controller simulator. And such controller simulator is exactly the same as the controller installed on a machine. Is exactly the same. The only difference is that the peripherals, so the I/O, like the input-output peripherals, are virtualized. So in a real machine, you have like the devices, like for making the piece, while in a controller, those are virtualized. So why these controllers are used is because when you are going to develop a code, like a program to produce something, normally you develop a code and you test the code on a simulator before bringing down to a machine, and maybe crashing the machine and make thousands of euros of damage. So for us, it was very much useful because we did the analysis on the controller first, and then when we were confident enough that we are not going to make huge damages on the machine, we did the experiment on the machines as well. Okay. So our search approach started in this way. We did a first high-level or surface analysis with traditional vulnerability scanners like Nessus, and so on and so forth, to see if there were problems related to the operating system, for example, running the controller or the libraries, generic libraries used by the controller. So this one was a kind of initial step. It was not much our focus. So the focus of the research was to look into the problems of the technology used by the controllers only, and specifically by the controllers of the CNC machines. So what does it mean? If someone comes to me and says, you know what, there is a controller running Windows and Windows is vulnerable, okay, interesting, right? But that's a problem of the operating system on which the controller is running. So for us, the goal was very much look into which kind of protocols actually, which kind of framework, which kind of libraries specifically to the industrial domain those controller runs, and which problem they have. So that's why we went down deep into looking at the technology used by the different vendors. And those technologies are used to connect the controller and the machine to the external world for the reasons I told you at the beginning, like monitoring the device, pushing new code on the machine, and so on and so forth. So to give you an example, Ethernet Q command is one of such proprietary protocol used by us. And the syntax is a bit like this one you have on screen. For example, with the command Q600, you can query for the value of a variable, so of a variable which is stored in the memory of a controller. For example, you can say, okay, what's the value of variable 10,000? Okay, you can do such remote RPC call to the controller. What you could also do, you could write a value into such variable, okay? So for example, with E10,000, 1, 2, 3, you say, you know what? I want to store value 1, 2, 3 into 10,000. And here you may already think from the security standpoint, so if you put a black hat and you say, okay, you know, I provide an API where anyone who's in the network can connect to my machine and write two arbitrary memory addresses on the machine, you might say, okay, that's probably bad, right? Because it's not something that would happen, should happen. So these are some of the cases we will see later in the presentation. Another protocol we look at is MT-Connect. So this is an effort made by different vendors to standardize all the different proprietary protocols. So there is a brand X, brand Y, brand Z, brand A, brand B. What happened, each vendor has his own dialect, his own set of proprietary protocols. MT-Connect is an effort to standardize all of that and use a semantic which may easily allow one vendor to talk to another vendor. Okay, this is still an open problem in the ICS domain, but MT-Connect is an effort. So most of the vendors we look at support MT-Connect with a goal to try to make the machine talking to each other. So after we did that, we look at the different protocols. There are way more than this. Of course, I will give you then all the reference. You can download the paper. It's like 80 pages of PDF. But I don't want to go into all the different protocols, otherwise it's going to be long. So after we look at all of this, we put our black hat and we say, okay, so those are the technologies offered by such computer numerical control machines. So what could go wrong here? So what we did, we developed a POC, like attack code. We test such attack code on the simulator and on the machines that we had access to. And then we found problems, of course, and we report the problems thanks with the help of CISA, the cybersecurity agency in the US. Cool. So let's go first, start from the top. I give you a kind of overview of macro problems that we found, and then we go into use cases. So I'm going to show you some demos of what criminals can do if they manage to connect to some of these CNC machines. So in general, we found, as you can guess, legacy software, okay? And I guess there will be legacy software for the next years to come in the OT space. That's a general problem in the OT and the ICS world. Another macro category of problems related to information and data leakage. What I mean is such controllers are bundled with frameworks and features for giving access to monitoring routines, so for monitoring those machines. But the result of that, sometimes they give out too much information of what actually would be necessary to give out. So criminals can abuse, we will see later in the talk, of such problems. Then there is a general lack of authentication or authentication often is not enabled by default. So that's super basic concept, right? So if there is no authentication, anyone which can connect to your machine can basically abuse of the service. And when there is a lack of resource access control, what I mean is that, for example, in normal computers, each process is separated. So one process cannot access the memory region of another process. Here is not the case. So often, process can jump from one memory address to another one. So there is actually a problem of access control of resources on the machine. So let me start with an example here, very easy, about how MT-Connect can be abused to leak the code running on the machines. So here is a dump of an MT agent that provides information on what the machine is doing. Is an XML. That's how MT-Connect works, because it is a way to, as I was saying before, to make different vendors talking to each other. So instead of having proprietary protocols, here it's a general language used by different vendors. And if you can spot it, I will offer you a beer. Let's see if someone can spot it. It's actually here. So one of the problems here is this vendor was leaking that piece of information. And I'm pretty sure you might not know what is it. I even didn't know when I started this research because I was not an expert in the domain. But that one is a code line it's actually a part of a source code of a program running on the controller. Those controllers, just as parentheses, they run programs that are developed in G code, or also called M code. So that's the language, right? As a C, Bash, whatever, Python. So in this case, it's G code. And every time the controller runs here in MT-Connect, he exposes the line that is currently executed in the program. And what an attacker can do, he can write, for example, in this case, I wrote a small script that query over and over the service and is able to extract all the code of the program running on the machine. I will give you some extra example later, but you can already see here the problem, right? So if you have an attacker that can leak and steal the code running on the production machine, he can basically understand what the machine is doing, right? So, and that's super severe, especially because G code is not compiled. So there is no actually need to take IDA or Ghidra and reverse engineering the code because it's uncompiled code. It's so easy to read. So this is one of the problems with leaking, data leakage. Another problem is that apparently vendors, they don't really care much about protecting their own asset. So this is a part of a controller simulator we look at. And this simulator had enabled a jumper that allow us to extract the firmware running on the controller. So if we take a look at the manual of the board running the controller, the manual says something like, okay, there is a jumper 27 that if you configure it correctly, you can allow the board to boot from a micro SD card. So what we did, we basically boot the controller with a kind of, it's called the BSP6. It's a bit like a Linux live OS for embedded devices, and of course that supports the architecture of this controller. And we managed basically to patch the controller, and then at that point we could basically connect the SSH to the controller, dump all the file system, and take a look at the code running on the controller. So I talked to the vendor, and they told me, okay, what's the problem if someone dump all the code on my controller? So you don't see the problem, right? I mean, you have to protect your asset, right? And for us, it was very helpful because at that point we could instrument the controller to monitor all the different attacks. So we had a footprint into the controller, and when we were doing the attacks, we were knowing what we were doing. Another big issue, as I was saying before, is the lack of resource access control. So this is the case for us. For example, on us, there is this proprietary protocol called the Ethernet Q command. Is the protocol I showed you before, where you could read certain memory addresses remotely, and you could also write certain memory address remotely. And if you take a look at the manual here, it says, you know what, with the E command, you can write macros. So macros in the OT world, in the CNC world means global register or global memories. And it says, you know what, you can write variables from 1 to whatever, 33, and from 10,000 to 10,999. And this is kind of helpful. I will show you later for in normal circumstances if you want to control a program remotely. I will give you some example later. So if you have like a parametric program, you can control the program remotely from a central server, which is okay. But the thing here is an attacker could actually do more than that and could write to other memory addresses, other macros. Here it's a short video that will show you how an attacker could disable the debug mode of the so-called single-step mode. It's basically the debug mode of a controller remotely. So you have a controller here on the right side. That one is a VNC client connected to the controller. So that's exactly what the operator sees on the machine. As you can see, when I will play, basically the controller will run in test mode. So this is used when the operator wants to test is the code that he has uploaded on the controller. So the operator needs to push the button each time to make basically you see here the code is moving one line by line, like in debug mode. And on the right side you can see that the controller is actually drawing things, so it's working, right? One line by one line. What the attacker does on the left, he connects to a service and he basically writes to a global variable like with admin privileges and said, you know what, I disable this single step mode, and they make basically all the controller running to the end of the code. So instead of having breakpoint on each line, basically I disable all of that and they make the controller running to the end. Of course, this creates safety issues because if operator is working on a piece and is testing the code and someone can disable this debug mode, then the machine just runs to the end and can easily crash the machine or create harm to the operator. So this is just an example, but it gives basically how the general problem here is that we have seen across all the different vendors. So there is a lack of resource access control, and attackers can write to global variable or variable that were not supposed to be written by normal users. So what's the impact here is huge. So we test all the different vendors here. There are all the different 4 vendors we test, and most of them are actually vulnerable to a bunch of attack classes. So compromise, like having a footprint on the machine because there is a vulnerability. Damaging, like either damaging the piece under production or damaging the machine itself with a huge amount of money involved into that. Cause a denial of service attack, so like blocking the machine while it's producing something, which is super bad. Because, for example, one vendor in Italy, I was talking with them, they said, you know what, we produce a car every 7 minutes. So if I'm an attacker and I block the production, you know, I can ask a ransom, right, to release the machine. Then hijacking, it means making the machine doing something different than what the machine is supposed to do. And then theft, like leak information out of the machine. So now I will give you tons of real-world example of attacks we conducted. So we start with this. This is how we usually use Metasploit against one of the machine to exploit a vulnerability that's back of 2010, like 30 years ago, to install a malicious application on the machine. This is an Okuma, and Okuma support the ability to install like plugins similar to a smartphone, where to a browser, where you can install a plugin in the browser. Here you could install like a plugin in the Okuma environment. So at that point, you take control of the controller and you turn the controller into, you install with such backdoor that connect back to our command and control server, and then at that point you can connect to the controller, read all the memory addresses of the controller. You could do pretty much anything, and that's super severe. In this example, for example, here I'm going to show you how you could change the geometry of a tool. So it's kind of more technical. So when the machine is operating, the operator needs to configure the machine saying, you know what, I'm using a drill bit, like the point of a driller, which is, 10 centimeter long, 5 centimeter long. So in this case is, if I read correctly, is 80, right? So the tool number 1, if you see there in orange, is 80. So there is a drill that is 8 centimeter long. What happens is, when the machine works, the drill gets wasted out because you're damaging the drill. After you do many drills, 1, 2, 3, you're basically damaging it. So there is this compensation factor. So the machine automatically adjusts the position in a way that the machine is still drilling at the same depth. So here we did an experiment where we developed a code saying, I want the machine to drill in a piece of metal 5 millimeter long, and then what the attacker did here was to influence the machine. So here you have a camera of a machine drilling a piece. Here we do the attack. So without doing the attack, the machine does create basically a hole into this metal piece of 5 millimeter .05. So what the attacker does, he injects basically an error of 0.25. You can see the difference of 4.80 against 5.05 is 0.25 millimeter, which correspond what you have on screen on the attacker console, you see here. So what the attacker does is inject such error. And what's the impact here? So if you're a criminal, or a bad actor, and you can influence the production and insert like a micro defects in a piece of in a piece that gets produced, that's super bad. So think of the company that is producing brakes, right? And you introduce a micro defect that passes the QA, then all these brakes get sold on the market, like thousands of pieces, and then you figure out that the brake it's not compliant with the specification, right? So it might break, it might create problems to the car and so on. And so the company has to recall all those pieces that are not compliant. So that's super severe from for a vendor. What an attacker can do can also introduce an error which is not 0.25 millimeters, so nothing. It can introduce an error of -10, I mean 10 centimeters. So at that point, the machine goes in compensation, and instead of just going up of 0.25, it goes down of 10 centimeters. So what happens, it completely breaks the point of a driller against the machine. So for this experiment, we use a 3D printer. We print the point in plastic, as you can see there in the left. So that's the plastic point. We ran the attack against a real-world machine, and we made the machine crashing the point against the piece. You can see there, that one is, I took it with my phone, a video, that's a frame of a video. You can see that the drill point is basically crashing against the machine. So this is an example of how you could write to a memory address that is used to control the geometry of a tool, and use such write to damage the part that you are building or the tool. This is the example I showed you before, where you could leak the source code of a program that gets executed on the machine. On the left side, you have a machine. In this case, it's an Okuma controller from Japan. You have the source code of the program that gets executed. And on the right side, you have the attacker console. So the attacker is regularly pulling the service asking for which line of code get executed, and then at the end dump all the source code of the program that get executed. So that's super bad as well, because you can think in a world where there are competitors, for example, two vendors, or both of them producing, I don't know, brakes of cars. Of course, someone can spy to another. So if he has access to the code that is used in production to create the piece, then he has access to the know-how of a company. So it's super bad. In this specific example here, there is a program that is used to drill 2 holes into a piece of metal, okay? And in the scenario we build up, you can see here in red, there is a variable called K that is used to control how many holes are written into the piece of metal. So this opens another attack scenario, that is attack scenario of hijacking a parametric program. So what happens, there is a feature that allows to influence what the machine is doing. So take, for example, here in the example here, you have a line that is producing thousands of pieces with a certain number of holes, whatever. So you can, the company can, using a central server, modify the code and say, you know what, instead of producing 2 holes, I produce 3 holes, or I produce 3 holes in a different geometry. And this is very common in production, because you want to produce pieces that are the same piece, but with different sides, for example. So a shape is always the same, but different sides. Here, for example, different number of holes. So there is a way to remotely, control the behavior of a program that gets executed on the machines. And here an attacker, what was able to do was to leak the source code, for example, which is already very bad. On top of that, was also able to influence the behavior of the program. So here you have a program running 2 holes. What the attacker does, he connects to the machine. He said, you know what? Instead, I change the value of the common variable 1, so of the memory register 1 that is used by the program, from 2 to 5. So at that point, what the machine does, it changes behavior. Instead of drilling 2 holes, it starts drilling 5 holes. This is just an example, but an example that shows how an attacker can hijack a parametric program that gets executed on the machine. The attacker can also rewrite the program that is executed remotely, so that's also super bad. So this one is I think it's a FANUC, this one. So you have this FANUC that is running this program called O1000, with just a name, right? So what attacker can do, he can download the program. Here we can see the program get downloaded. He edit the program, adding a stupid comment, for example, and changing the number of the program into 1002. And here what happens is you can upload the program, and the controller doesn't notify nobody basically of the attack. So the controller switch to the new program, and for the next execution, run the program hijacked by the actor, by the bad guy. Okay, super bad. Here is another example of how an attacker can damage the part, so the piece that get produced. So here the attack consists of hijacking the advanced management tool system. So what happens when you are producing a lot of pieces, one after the other, you are going to waste out your drill point, as I was saying before. So when a tool is exhausted, you replace it and you put the other one. When the other tool is exhausted, the machine replaces and take the next one. What the attacker can do, can reset remotely that index, so that count how many holes have been made with one drill point, and make the machine always using the same tool over and over, so ever burning the piece that is producing, which is super bad, or making like the machine basically, damage basically the machine itself. Attacker can also disable the feed hold, that's super bad. So the feed hold is basically the red button you can see there that the operator can press if there is something wrong. It's basically like the stop function or the brake of your car. Like I'm driving, I'm almost crashing against a wall, I want to brake. So we manage to basically hijack that, and if the operator press the button, the machine says, do you know what? The feed hold is suppressed, like, I'm not going to stop the machine. So there is a way to disable this safety mechanism introduced by the machine. There is also a way to leak manufacturing information. So here it's our Okuma in a real world scenarios with a vendor operating. So we made the attack, we start monitoring the machine, we managed to leak information like, okay, the name of the machine, the serial number, which kind of code get executed. In this case, is a test 6 is the name of the program code get executed. The status, if it's running, not running, the source code, each line that gets executed on the machine, and the number of pieces that the machine produces. So that's also bad because an attacker can spy on the production and know, which pieces are produced, with which code, by which machines, in how much time, and so on and so forth. An attacker can trigger software alarms similar to IRQ, like software alarms in the operating system, and that would block the production. So it can basically ransom a production by saying, you know what, I'm going to trigger software alarm, and I block the production. Operator need to come and reset the machine every time. So it's possible to trigger software alarms remotely. And it's also possible to take control of the machine by installing a ransomware that would lock the machine, the user interface, to ask a ransom. So that's also very bad. I hope I convince you that there are multiple use cases and scenarios that someone can build up based on all the vulnerabilities we found. This is because CNC machines are a very complex system. And of course, the fact that there are multiple vendors and players involved doesn't really help, especially because there was a strong push into introducing all these new protocols to enable connectivity on a large scale, so-called Industry 4.0, but without taking security as a first driver. This is also shown by our responsible disclosure that went very long. So it took us about 9 months to have this problem fixed. Even not all of them have been fixed yet, but they are probably going to be patched sooner than later, and I have to thank CISA for supporting us in dealing with vendors, because often vendors, they were not really understanding much what we were doing and the impact of the problem we have identified. So we had to explain them and train them on the problems. And that's also, I think, part of our work, to raise awareness in a domain where security is not yet understood. There are countermeasures that can be put in place while things get fixed, starting from correctly segmenting your network and not exposing CNC machines to networks that should not have access to. Of course, there are commercial tools, IDS and IPS, that have support for OT protocols. We collaborate with some of these vendors, and if you buy now the modern IPS, they have like filtering rules for monitoring OT protocols like Pattern of Us or MT Connect, and if there is an ongoing attack or leakage, they can prevent it. Of course, patch management, so consider those machines as part of your IT asset, so regularly patch CNC machines because they run a very complex operating system like normal computers. There is more of that, of course. This is just a presentation, so if you want to know more about security implication of modern CNC machines, there is a paper online. Just Google for that. It's called The Security Risk Faced by CNC Machines in Industry 4.0. And it brings my name and the name of my co-authors, so you can easily download that. There are also a few videos that we put up to show all the different attacks in place, which is very cool because they are real-world videos we took on the production line with the machines. So that's all for me for now. I still have a few more minutes, so I'm open to questions, and I thank you for your time here with me today. Thank you.